Welcome, everyone, and welcome to Dana-Farber's Department of Data Science Frontiers in Biostatistics webinar. My name is Erica Fike, and I am the program manager for the department. If you have a question for the speaker or the organizers, please use the Q&A tab, or you can raise your hand. Our faculty organizers will manage the Q&A session during and after the talk. With that, I will turn it over to Nabia Tayob, who will introduce our speaker today.
Thanks, everyone, and welcome to today's seminar. I have the pleasure of introducing Malka Gorfine. Dr. Gorfine is a professor in the Department of Statistics at Tel Aviv University in Israel. Her research interests are in disease risk estimation and prediction using candidate genes and environmental risk factors from both family and case control survival data, statistical genetics, non-parametric statistics, biostatistics, and machine learning. Just a note for anyone, there's a postdoc fellowship on her website if anybody is interested, so take a look at that. We're pleased to welcome her today, and she's going to be talking about optimal Cox regression subsampling procedure with rare events. So looking forward to it. Thanks so much for joining us.
Thank you very much. Thank you for inviting me, and thank you for the nice introduction. This talk is mainly based on the work of my PhD student, Nir Keret, that is now going to start a postdoc position in Seattle. And the second part of the talk will be work also with Taragasi, a master level student. I would like to start with the motivation and the goals. Massive sized survival data sets are becoming increasingly prevalent with the development of the healthcare industry. Such data sets pose computational challenges unprecedented in traditional survival analysis use cases. Still, Cox proportional hazard regression is one of the most popular statistical models for the analysis of survival data to date. So today, I would like to address the setting of right-censored and possibly left-truncated data with rare events, such that the observed failure times constitute only a small portion of the overall sample. And I would like to consider the Cox proportional hazard regression. We provide an optimal subsampling procedure that approximates the full data estimators, and we have also created tools to ascertain the necessary subsample size based on different criteria. The motivating example is the UK Biobank data, and in particular, we are going to analyze the colorectal cancer data of the UK Biobank. The UK Biobank is a large-scale health resource comprising genetic, environmental, and medical information on approximately 500,000 volunteer participants in the UK, recruited at ages between 40 to 69 during the years of 2006 to 2010. The participants have undergone various measurements, provided blood, urine, and saliva samples for future analysis, and have also provided detailed information about themselves. The main idea of the UK Biobank project is to continuously monitor the health and well-being of the participants until the end of their lives. So the data is extremely rich and of a high value. The colorectal cancer is the fourth most common type of cancer and the second most common cause of cancer-related death in the UK. And since the recruitment strategy of the UK Biobank started at age 40, it is very important to know that having colorectal cancer before age 40 is very rare. So the fact that we estimate survival of colorectal cancer based on this data does not cause any bias. Of course, we have right censoring in the data. Out of the almost 500,000 participants with available genetic and environmental data, there is a total number of only a little bit over 5,000 colorectal cancer incident cases, namely those who developed colorectal cancer during follow-up. And of course, as the study continues, the number of incident cases will grow. Currently, the number of right-censored observation is over 480,000, which is a huge number. We also have left truncation, so each subject is recruited at age between 40 to 69. So only individuals who survive by their recruitment age are sampled, and of course, we should also take this into account. The data that we usually have in survival analysis, we denote by VI the age at colorectal cancer diagnosis. CI is the age at right censoring. TI is the minimum between V and C. XI is the vector of covariates, and delta I is the failure indicator. It takes the value of 1 if we observe the event time and 0 otherwise. The Cox model is usually formulated by a baseline hazard function, unspecified baseline hazard function, lambda 0, and the exponent of beta transpose X, where beta is a vector of unknown regression coefficient, and our goal is estimating beta and estimating this unspecified baseline hazard function. Usually in Cox model, we estimate beta by maximizing the partial likelihood, and then we estimate the cumulative baseline hazard function by the well-known Breslow estimator. Now, it is well known that most of the information in survival data is provided by the observations with observed event, i.e. the non-censored observations. And in our setting, as I mentioned, we have about 480,000 participants, and only about 5,000 of them were observed with colorectal cancer during the follow-up period. So if we would like to save computation time, it makes sense in such a rare disease setting to keep all the colorectal cancer cases and then subsample only among the censored observations. Nevertheless, the Cox-PH package of R demonstrates remarkable efficiency and enabling analysis of 500,000 observations to be completed within minutes. So we don't need any fancy subsampling procedure for this data set as it is now. However, frequently the proportional hazard model assumption of standard Cox model is breached, and instead a time-dependent coefficient model is expressed. So instead of having lambda 0 times the exponent of xi times beta, we now replace beta with beta t, where the regression coefficient is a function of time t. So the widely used Cox function, cox.zph, again, it is part of the survival package in R, offers a diagnostic plot to facilitate the comprehension of time-dependent effect. So, for example, in our colorectal cancer data, when we applied the Cox model with 500,000 observations, then what the result of the cox.zph provided here in this plot for the covariate sex. What you see here is the blue line is the fixed effect, where we assume just the beta, But then we have a spline-based estimator, which is described by this curve with confidence band with the dotted curves. And you see that there is a huge discrepancy between the blue line and the black curve. So this plot suggests a time-dependent effect for sex is required. Now the question is, how do we fit a time-dependent effect within the Cox model? So the most popular approach is actually to assume that beta T follows a simple functional form. And actually this plot can suggest us what type of functional form we would like to assume, or not we would like, what is reasonable to assume. And then we can trick a regular Cox model program into performing the fit. In our example, we employ beta T equals beta, and then we have this function log of T for T less than 65 and log of 65 for T greater than 65. Why? Because we see here an increase, and then at around 65, it is becoming more or less flat. Now, this formulation, this functional, transforms the problem into a scenario with time-dependent covariate, because previously we had time-dependent coefficient, but now we transformed the problem to a time-dependent covariate. This is the time-dependent covariate, but now we have fixed coefficient, which is actually an easy problem. So now we formulate the model in this way. We have still the baseline hazard function. Beta is now, we go back to have beta instead of beta as a function of T. And we have xi of T instead of x. The well-known simple way to code time-dependent covariates with Cox regression uses intervals of time. What do we mean by that? Each observation is partitioned into time intervals between all observed failure times in which it was at risk. So if I entered the study at age 40 and left it at age 85, instead of having one line in the data set, my follow-up time is partitioned by the observed failure times, with all observed failure times that are determined based on all the other observations in the study. And instead of having only one line in the data set, I have now multiple lines. Each line represents a different interval. So this partition of the data results in a large number of dummy observations. I had one line in the data set, now I have multiple lines. The UK bi-colorectal cancer analysis started with 500,000 observations, is turned into a data set of about 350 million dummy observations. So I started with a relatively small data set, and now I ended up with a huge data set. And then, as Terry Thurnew, the father of the survival package in R and many other excellent works, as he wrote in one of his papers, one common question with this data setup is whether we need to worry about correlated data since a given subject has multiple observations. The answer is no, we do not. The reason is that this representation is simply a programming trick. The likelihood equations at any time point use only one copy of any subject. The program picks out the correct row of data at each time. So we know how to analyze this, and actually it is very simple. The only issue is that now we have a data set of a size 350 million observations or dummy observations. So again, back to our colorectal cancer data, we started with about 5,000 colorectal cancer cases, only less than 500,000 censored observations. We are going to analyze about 180 covariates, including well-known SNPs and environmental risk factors. And then, because a diagnostic suggested a time-dependent coefficient, then our data set, instead of being of 500,000, it is now of a size of 350 million rows, but the number of cases is not going to change. It is still the same number as in the original data set. So if we analyze now the Cox model based on this data with this number of covariates on Amazon cloud, it takes about 14.5 hours. A small spoiler, with our optimal subsampling technique that I will show in the next slides, the running time is less than 3 hours, with a minimal efficiency loss, if any, while being memory efficient. So now I hope that I convinced you that I have a good motivation for providing optimal subsampling procedure. So again, this is the notation that I introduced earlier. And the estimating equation based on the partial likelihood estimator can be represented based on the full data before doing any subsampling, can be written in this way, where we have the summation over all the observations. We have here the event indicator, and the function h here is, of course, a function of beta and a function of the vector of covariates and the observed time of all the observations that are still at risk at the observed event of subject I. H is a nonlinear function of beta, and usually Newton-Raphson algorithm is utilized. For example, in the survival package of R or the lifelines of Python. So what we propose is actually, instead of using this estimating equation, we would like to move to a weighted Cox estimating equation, where we go over a subsample Q, and each term within this summation is multiplied by WI. What is Q? Q contains all the observed events plus a subsample of size Qn of censored observations. So again, because we are using a rare event, we would like to keep all the 5,000 cases. We would like only to take a subsample out of the 300 million observations or dummy observations that are censored. What is WI? WI is defined to be 1 if the subject is not censored, and is defined to be 1 over PI times QN if the subject is censored. And now we need to define what is PI for each observation, and we would like to have PI to be optimal in some sense. If we do not take an optimal, but for example, we take a uniform sampling, then if the number of censored observation is denoted by NC, then PI is, of course, 1 over NC, and then WI is just NC divided by QN, where QN is the size of the subsample from the censored observation. So now, and I will show that uniform sampling is possible, is fast, but it's not optimal. And instead, we would like now to determine optimal subsampling probabilities under several criteria. So before presenting the optimal strategy, a good question could be, why would I use subsampling instead of replacing the standard Newton-Raphson algorithm with a stochastic gradient descent? So the main answer is that the function COX-PH in the survival package of R, and it's similar in Python, includes a rich collection of high practical and important features. And this is only a partial list. Stratified analysis, time-dependent covariate, time-dependent coefficient, both of them together, various features about goodness of fit, competing risk, weighted analysis, random effects, and many other features. So if I replace the Newton-Raphson by a stochastic gradient descent, it means that for every feature, I need to reprogram and write a new code. If I do subsampling, I do it once, and then I can analyze the data and use any feature of the COX-PH by using any feature of the COX-PH function. So in case a huge set of sensor data is indeed useless, a subsampling approach seems a better way to go instead of using stochastic gradient descent. Okay, so if we would like to use subsampling, now we need to discuss, are we going to do it with replacement or without replacement? When sampling without replacement, after each drawn observation, the remaining sampling probabilities should be updated. This could be very complicated and can take a very long computational time. So for simplicity, the method and the theory are developed for sampling with replacement. Practically, since the number of censored observation, the ratio between the number of censored observation to the subsample size is assumed to be very large, because QN is going to be much, much smaller than NC, there should be very, very little difference between sampling with and without replacement. So we are going to do it with replacement. Okay, so then we have an estimating equation. We have any type of sampling probability. And then for any WI in the conditional space, i.e. given the observed data, we were able to show that beta tilde is converges to the estimator of the full data partial likelihood, which is a very good property. And this is where we condition on the observed data. Then the next step was to show the asymptotic properties of the beta tilde estimator, the subsample estimator, in the unconditional space. And then we showed that under some regularity conditions, beta tilde is a consistent estimator of the true value of the regression coefficient vector. And also it is asymptotically normal. And we were also able to provide the a closed form for the variance matrix. The variance matrix consists of two terms. One term is the variance of the full data estimator, and additional term is this one, which is also a function of the variance matrix of the full data, but here is an additional term which is a function of the sampling probability and of course the vector beta. If one is interested in the exact expressions of these two matrices, you can refer to our paper. But it is, since this expression is non-negative, we see that doing subsampling is, of course, increasing the variance as expected. So what is how can we use this variance? Given the explicit expression of the asymptotic variance, now we can get optimal sampling based on some criteria, for example, to minimize the variance. So here again, you see the variance expression, and we're going to use two optimality criteria, the A optimality and L optimality. A optimality is minimizing the trace of the variance, and the L optimality is minimizing only the expression that is the trace of this phi matrix, because only this matrix is actually a function of P. We will see that A optimality provides a smaller variance than the L optimality under the same size of subsample, but the A optimality takes more time to calculate than the L optimality. So there is a trade-off. Then once we formulate a criteria, an optimality criteria, now we can then derive the exact probabilities. So under the A optimal sampling probabilities, the vector of probabilities is defined by this argument for all censored observations, and the L optimality is this expression where you can see that PA, which I said is going to provide a smaller variance, it takes into account the covariance matrix of beta hat, but the L optimal criteria is not including this covariance matrix, and this is why PA will take more time, but and PL will be faster, but PA would provide a smaller variance. But an important issue is that both are function of the unknown vector of coefficient beta 0. So the above results are impractical as they contain the unknown beta 0. Instead, a two-step procedure is implemented. In the first step, we are going to have a smaller subsample based on uniform sampling from the censored observation, join them with the events, estimate the regression coefficient based on a crude estimator, and then estimate the sampling probabilities, PA and PL. In the second step, we sample another QN set of QN observations from the censored observations, but now here we did the sampling from based on uniform sample, but now we are going to sample QN observations based on the probability that we approximated in step 1. Once we have this a subsample of the censored observation of size Qn, we join this observation with the observed failure times to form Q. We run weighted Cox regression on Q to obtain the two-step estimator. We denote it as beta tilde TS. So the following theorem establishes the asymptotic properties of the two-stage estimator. So it is a consistent estimator to the true regression coefficient vector. And again, we have a closed form for the variance estimator. So now we need to discuss the computational complexity of the beta tilde estimator of the two-step procedure. Since we are including all the observed failure times in the analysis and assume that the number of observed failure times constitute a small proportion of the overall sample size, and since it is assumed that the number of events divided by the total sample size and the subsample size divided by n converge to small positive constant as Q and n goes to infinity, we cannot use big O notation in order to express the expected reduction in computation time, since, of course, big O of alpha n is a big O of n for any fixed alpha. But we demonstrated by simulation and real data analysis that in practice, our method results in substantial computation time reduction. For example, it takes only less than 3 hours instead of more than 14 hours. We also show that our method can be extended to more complicated analysis, delayed entry, left truncation, stratified analysis, time-dependent coefficient, time-dependent covariate, and so on. We also show something very interesting, I think, in the paper, but I don't have time to go into the details. So in case the data set is too big to fit into the RAM of a standard desktop, we provide a memory-efficient batch-wise reservoir sampling type procedure. So if one is interested in these details, you should go to directly to the paper. So here are the results of the data set. So we had about 350 million observation, 180 covariates. We applied the subsampling methods with Qn at the size of 300 times the number of events. So it means that the data set that we eventually analyzed consists of only about 1.6 million, instead 350 million. So the full data analysis, the runtime is above the 14 hours. L-optimality criteria, it takes 4 hours. L-optimality with the reservoir sampling that I mentioned before, that I mentioned here, without going into details, it took less than 3 hours. A-optimality took much longer than L-optimality, as expected. The L-optimality with reservoir is now not bad. The uniform sampling is only half an hour. So in terms of running time, of course, the uniform performed the best, but in terms of accuracy, of course, uniform is not that good. So we compare the results of each method by looking at the L2 distance between the estimators of each method compared with the full data. So this is why the L2 distance of the full data analysis is, of course, 0. But then you see that the L optimality is 0.029. The L optimality with reservoir is 0.026. A optimality is better, but the runtime is much larger. And the uniform in terms of L2 distance is not so good. So the L optimality with reservoir sampling offers a good balance of runtime and accuracy while being memory efficient.
Sorry to interrupt you. Can I just ask a quick question about in the two-step procedure you described doing a uniform sampling to get an estimate of your beta 0 and then doing the weight estimates? What's that size of that Q0?
Okay, so this is a great question. So when we this work is published in JASA, and then in the JASA paper, what we did, we took, here I write Q0 and QN, but actually what we did is actually we took the same size, QN here and QN here. But then in a work later, not yet published, but I will show some results of this work, we actually ask what should be the size of QN and what should be the size of Q0. And what we discovered is that Q0 could be very small. It could be like a small C multiplied by the number of events. C could be 5 at most. This should be good enough. However, QN, this is a very crucial question, an important question, and I will answer it later on. Another way to present the results, here we show the estimated coefficient based on the optimal subsampling methods and how they are agreeing with the full data partial likelihood coefficient. So what we see here is in the x-axis, we see the 180 coefficient, and here we see the difference between the estimator based on each method minus the estimator based on the partial likelihood. And what we see is, and the red lines are for the uniform method. The green is for the A optimality criteria with the reservoir, and the blue is the L optimality criteria with the reservoir. It seems that the best fit is the green. The blue is not so far from the green, but the red seems to be the worst in terms of difference from the partial likelihood estimator.
There is a question in the chat. Is there a relationship between this weighting, covariate balance, and propensity score weighting?
No, not at all. Not at all. So this is an interesting question. So what happened is that if we go into details and analyzing what observations are getting a large weight and what observations are getting smaller, large probability, and what observations are getting smaller probability. So in general, it is like that. Observations with extreme covariates are going to have a relatively large probability. Because we would like them to be represented in the sample. And observations with large follow-up time It could be censoring or, okay, we only look at censoring. With large follow-up time, they are also going to have a large weight, large probability sampling. But it has nothing to do with propensity score. Yeah. Okay, so once we have a machinery for applying subsampling, the next question is how to choose the subsample size, QN. So our primary goal is to reduce computation time, and we equally committed to maintaining the necessary statistical significance level for answering our research question and avoiding a significant increase in standard error. So defining QN is actually very important. So we, in another work, we provide tools to facilitate the selection of some sample size QN. So we start with defining the subsample size based on a measure that we call relative efficiency. So an estimator of relative efficiency can be defined in the following way. What you see here in the numerator, what we have is the variance of the two-step estimator, and in the denominator, we have the variance of the full data. And we use here, because the variance are matrices, we use the Frobenius norm. So since this expression, as we mentioned earlier, is positive, then the lower limit of this relative efficiency estimator is expected to be 1, which corresponds to the situation of using the entire data and therefore not losing any information. If one is specifically interested in the effect of particular covariate, the above can be easily modified to focus on the relative efficiency of this particular covariate instead of considering the entire matrices. But the relative efficiency estimator, as defined here, is actually possess practical challenges. The first one is that it includes the estimator based on the full data, which we aim to avoid. So we don't have this. If we have this, all this project is redundant. And then it also involves estimating the regression coefficient based on the two-stage procedure, but this can be computed only after we determine the size of QN. So these two challenges can be easily solved by using the beta tilde U that we have from the step 1 of our procedure. Now, so if we replace each beta here in the numerator and the denominator by beta U, we still need to calculate these two matrices, both of which involve the full data. So we can replace these two matrices also by additional subsampling stage, and we call it step 1.5, and then we resolved all these challenges. So now the subsampling, our estimating procedure is to apply step 1 as before. We sample Q, 0 observation from uniformly from the censored observation, join them with the observed failure times to form Q pilot, run a weighted Cox regression on Q pilot, and obtain beta tilde U, and then use it to derive the optimal sampling probabilities. In the new step 1.5, we sample Q0 observations from the censored observations, but now we are going to use these optimal probabilities from step 1, combine them, these Q0 observations with the observed failure times, and we have Q1.5, and then we can compute these two matrices. We need to compute them only once. This is why this step is very fast. And then we plot the relative efficiency curve as a function of Qn, and we choose the minimal Qn that provides the required relative efficiency. Step 2, once we have chose Qn, then we continue with this size of Qn, and step 2 is exactly as before. So here I would like to show you the relative efficiency analysis on the colorectal cancer biobank data. Just to remind you, we had 350 million dummy observations. We had about 5,000 observed events. The earlier analysis relied on Qn equals C times NE, where C was 300. So it means that the previous analysis was based on about 1.6 million observations instead of 350. Nevertheless, the relative efficiency analysis suggests that a considerably smaller sample size would be adequate. For example, C could be, instead of 300, it could be only 50 or even smaller. How can I see that? So you see here 3 plots of the relative efficiency curve. The red line is at the value of 1. And what you see in the y-axis is the relative efficiency as a function of C. So you see that for small value of C, of course, the relative efficiency is low. And we would like to take a value of C that would give us a relative efficiency close to 1. This is for the method of A optimality, L optimality, and uniform sampling. So we see that for C equals 50, the relative efficiency is already very close to 1. Definitely for 100, and we took 300. For L criteria, the L optimality, the efficiency is not as close to 1 as it is here, but it is still quite close. The uniform is not optimal, and this is why even under 50, it is not close enough to 1. Some concluding remarks. We have proposed efficient and fast subsampling-based estimators for the Cox model, motivated by 2 optimality criteria under the setting of rare events. Please refer to our paper for the reservoir sampling. We believe that this work stands as a cornerstone for the development of subsampling methods for other Cox regression-based methods, such as frailty models, correlated data, recurrent events, and multi-state models, and more. I presented here a relative efficiency-based tool for choosing the subsample size Qn based, but it was based on relative efficiency. In our work, it is not yet published, we also consider the required subsample size for achieving a specific power in hypothesis testing problem. I did not show simulation results, but if one is interested in seeing our simulation results, there are a lot of simulation results in the paper and supplementary material. The subsampling paper is published in JASA 2023. The R code for the data analysis and reported simulation is available at this GitHub site. And upon request, a draft on the optimal subsampling size QN can be provided. Thank you very much. That's it.
So we have another question in the chat, actually. Could you do this with a min-max optimization criteria where you want to minimize the worst case error in the estimation of the beta?
Oh, this is interesting idea and interesting question. It would require do all the work from scratch. So yes, definitely. It is a very interesting question. Thank you very much.
I had a question, if you can go back to while we wait and see whether any of the other attendees have some questions.
Sure.
Can we go back 2 slides, I think it is? Yeah. So I had a question about the runtime. Like, what's the difference in the runtime with C equals 300 versus C equals 100? Like, you had presented that for, it was about 10 hours for the A optimality, for something for the L. And then if you do your other method, you drop it down to 2.75. But if you did C equals 100, like, how much are you saving by doing that?
Right. Okay. So this is actually a very good question. The runtime between 300 and 100 would be relatively small. It will be like half an hour or something like that.
Okay.
But still, you need to, I think that one needs to have a tool to decide on QN. When we analyzed the UK Biobank by this method at the first time, we had no idea how much how QN should be defined. What is the size that we won't see huge differences between the estimators of the two-stage estimators and the partial likelihood the full partial likelihood estimator and so on. But yeah, I completely agree with you that between 300 and 100, the differences are marginally small. Yeah.
And I guess the whole point is when you don't want to have to run the full partial likelihood in practice when you're applying this in another setting. So you did it obviously because you're trying to develop the method, but that's the whole point. You want to avoid the 14-hour runtime.
Exactly.
So you don't know what C
Exactly. And I think it is important to know that when we run the UK Biobank data analysis on Amazon cloud, it took us more than 14 hours. But usually when we do data analysis, we don't run it only once. We do it one time, and then we see, oh, the definition of this variable was not accurate enough, and we run it again. Several times of 14 hours. It is a lot of money.
Yeah.
So it is important to have a rapid way.
We have another question. What is the consequence of Cox model misspecification if it has double effect on the estimation and the sampling as well?
So this is a very good question. If the really good questions you are providing here. So if we have a misspecification, then it means that the sampling probabilities are not optimal. I said they are optimal under A criteria, they are optimal under L criteria. They are not going to be optimal. They are going to be close to optimality, depending on the discrepancy between the true model and the proportional hazard assumption. However, this unoptimality of the probabilities are not going to cause to cause bias because we are weighting by the probability that we are using. The bias is going to be just because the Cox model is not the true model, as you have in the full data analysis. So by using this procedure, if the model is misspecified, we do not cause additional bias.
And then there's another question. It will not take much time in multi-stage survival analysis for 50K data. Then we should go to your proposed method. I don't quite understand the question. Maybe you do.
Not really.
Yeah. I don't know whether the person can elaborate a bit more on their question.
So if it is only 50,000 observations, the survival package in R is so fast, then no need for subsampling. Then don't go there. Although I would be happy to see that you use my method, but don't. Unless this 50,000 now require a time-dependent coefficient or time-dependent covariate. Then the data could be expanded dramatically, and then there is a need for subsampling, and then you are mostly welcome to use our methods.
Okay. Well, we're at the hour, so thank you everyone for participating. Thank you, Dr. Gorfine, for joining us. This was very interesting. We enjoyed it so much, and thanks very much.
Thank you. Thank you very much for having me and asking great questions.
Take care. Thanks, everyone. We will see you guys again in January. We will be hosting Dr. Rod Little in January. Thanks.
Bye. Thank you.
Bye.